Alright, so you don't have any homework. It makes you feel better, Brecken. They were complaining to me how life is boring, at least some of them without you here. So they may be faking it, at least for the video, but some of them, at least some of them. Alright, so I think we have enough turns to merit the dart game today. Sorry, Brecken. So we're going to go ahead and play that. You didn't have any homework. Alright, so go ahead and get that piece of paper that's going to write down stuff. You don't know. The other classes swear that the blue darts are better than the red darts, so that's up to you, but you're going to get Germex before you come up here, that way you don't corona my darts. So we will do it that way. Also, I'm going to have to slide it up towards the ceiling because technically, we're not supposed to, we're trying to not get y'all in video as much as possible. Now if you're stupid and if you go dancing in front of the camera, that's your own fault. But someone remind me once the game is over to shift the camera back down because I made Jamie watch the ceiling for like 30 minutes one day by accident, so we're not doing that. So someone remind me once the dart game is over to bring it back down. What?
They said you were lying. That was the wrong people.
Alright, we'll just start with Kendall. We'll work our way around. Alright, Kendall, what is the ability to do work? Good job. Come get your non-corona. No. It's 2. I know that's 2. I basically allow a practice shot. Yeah, we'll say this line right here, so that's a good even mark for everybody. Okay, well it's still there. Hey, it popped up into 17, so that's good. So that's better. Alright, Maddie's turn. Alright, Maddie, what's the SI unit of energy? Joule, come get your Germex. I'm making sure there's no corona. No slipping on the floor.
Don't tell me that.
Good arch. Alright, 16, Gavin. Alright, Gavin, there are 3 basic types of energy. What is the energy of motion? We are currently using this. Kinetic. Well, this is like a ritual. So you have to get your next for. 5. I can't see what that number is, but it's solid in the center. 3. So 8, not bad. Alright, Audrey. What is the energy of the electromagnetic spectrum? So it's light, radio waves, X-rays. Good enough. Not bad. Oh, let me see. Yeah, it's on 13. Alright, Noah, what is the energy associated with the forces acting upon an object from, like, its position standpoint? What is the energy associated with the forces acting on an object? Like, if I were to raise this up, it doesn't have energy right now, but if I were to let go, potential energy. Oh. Don't contaminate. No touching your face after this, otherwise you get extra Germex. You're dead, Noah. You're dead. Oh, it's a good try. Yes, and 7. Alright, back over to Kendall. Alright, Kendall. There's another way to divide up energy. What do you call the type of energy that affects the whole body of the object? Alright, we'll just go to the next person then. Alright. Chemical? Okay. Nope. I didn't know if you were changing your answer. Alright, we'll say that the question is dead at this point. Alright, anyone notice for fun? Go. Mechanical. Alright, Maddie's question officially then. Alright, Maddie, what do you call energy that affects the atomic and molecular level only? Yeah, basically.
No.
Non-mechanical. Come through your darts. That's a good try. That's a good try. Alright, Gavin's turn. What is the law that says energy specifically is neither created nor destroyed? Energy is neither created nor destroyed. Audrey?
Did you say it was a law?
It is a law.
Law of conservation of energy?
Law of conservation of energy. Did you know as soon as I moved on? I'm sorry. You gotta know as a bastard. Okay, she gets to rethrow if you do something to distract her, so don't be doing stuff. Alright, now it's turn. What is the law that says that matter and energy are neither created nor destroyed?
Matter and energy.
Matter and energy.
It's a law.
The law. I'm not helping you. You don't deserve to be helped if you don't know what this means. That matter and energy can neither be created nor destroyed. Alright, Kendall.
Law of conservation of matter and energy.
Yeah.
That's what I thought it was.
Law of conservation of matter and energy. I think you just overthought it, or you were so focused on trying to get Audrey to miss that you forgot what the previous question was and weren't paying attention.
I should think it's right.
Don't second guess yourself. 10. That was a good try. Alright. Alright, since energy is energy of motion, you also have whole body kinetic energy. Alright, so different types of kinetic energy. What is the energy of motion? We'll put it this way. So if you're moving in space, so it's a specific type of kinetic energy. It starts with a T. A T. Like a little ball, how like we threw it across the room, a little hacky sack. Alright, you having a chance to seal? Translational kinetic energy. And then it causes translational motion, or that movement through space. Alright, start. So a translational motion with translational kinetic energy. Okay, it's right in line. So 4 or repair. Okay. Alright, what is the equation to find kinetic energy? I think this is your turn, Audrey, but I think you might have been, I think you left right at this point.
This is start with an E.
K specifically.
M. This is a guess. B. 4.
Final answer? You're missing one thing.
Yeah.
1/2 mc squared. Alright, go ahead and throw it down. You were thinking of this one. That's the one with Einstein's theory of relativity. Let's see. Alright, we talked about other types of kinetic energy. What type of kinetic energy is it? Whenever you stand there, you're just spinning. I mean, it's kind of weird. What is that? This is like the Earth spinning, or like you spinning. So you're standing there just spinning in a circle. You see this? You see little kids do this more. You don't see big kids do this a lot. Alright, Maddie, you can't steal. R. Okay, well, Kendall gets it back then because that's an unfair advantage. Okay. Rotational kinetic energy or rotational motion. You can think of it as like how the Earth rotates, same idea. Come through. kinetic energy is that whenever you're moving in a circular path, so the Earth is going around the sun, is what we call that. See? Alright? Yeah, so circular motion. Oh my,
What should I
okay.
say? Oh no.
Alright. More than 5. Alright, there are 4 factors that affect rotational kinetic energy. Sorry, name one.
Speed.
Probably one I asked. Yes, actually, speed is one. It might fall, so we'll see. Or not. Okay, so 4 and 2. Alright, no, what's another factor of rotational kinetic energy?
Time.
No. Size, speed up. So size, speed.
Oh.
I'm not sure if just increasing the kinetic energy necessarily increases the accuracy. Okay, 50. Alright. Maddie, what's another part of rotational kinetic energy? Math, speed up. You know what's coming, Gavin. Good try. Good try. Alright, what's the last one? So we said mass, size, speed. Shape. Good job. So if you have a wonky shape or if it's not as solid as another one, it won't affect it. I'll say it's in the line, so you can have 5 or you can rethrow. Alright. Audrey! Alright, what do you call the energy that an object possesses due to the random motion of its particles? Starts with T. Alright, Noah?
Repeat the question.
What do you call the energy that the object possesses due to the random motion of its molecules?
What do you mean? Like,
So, the molecules are vibrating. So what do you call the energy that it gets from the motion of those particles?
so it starts with T.
Starts with T. I don't think I can give a hint without giving it away. Alright, Audrey, do you want to guess? You have 15 now.
Is it translation?
Nope. Couple seconds now. What the question said. Alright, anyone know? Alright, thermal energy. So thermal energy is the energy, basically it's heat energy. So as you have the molecules vibrating, they're generating heat. That's putting you on a slight temperature. Alright, Noah's turn officially. What is the energy caused by the disturbance moving through a substance? Look at this water specifically.
Supposed to start with
W.
wait.
Wave energy. Good job. Seven. Alright, add up your points. Who got, we got a couple of high numbers, so who got 30 or more?
That's tough.
Did you get 30 more, Noah?
I got 14.
Alright, don't forget your candy Kindle. Alright, go ahead and get out your notes. I'm gonna move my chops so I don't forget. Alright, so fundamental forces and potential energy. Go ahead and look over on page 76. So we're talking about potential energy. What is potential energy? Maddie. translational motion because the energy is being transferred from one object to another. You're all fired, by the way, because you didn't remind me. Sorry, Becky. Sorry. Okay, so potential energy has to do with energy associated with the object and the position of the forces on that object. So position of the object with the forces acting on it. So right now, you are on Earth. Hopefully you realize you're on Earth. And that is what's holding you to Earth. Now, your book points out that there are 4 fundamental forces in nature that these forces cause potential energy. The first one is gravitational force. This is an attractive force between all material objects. Now, thinking through this, Kendall, are you a material object? Are you made up of matter? Yes. So if you are made up of matter, why does your marker not stick to your hand? Since the gravitational force is an attractive force between all material objects. Why does it not go zoom? But what happens if you, why does your pen or highlighter or whatever you're holding, whatever your hand upside down, why does it fall? Why does it not stick to you if it is an attractive force between all material objects? But why does gravity pull it down as opposed to go to you? But why? Why does this stuff not just go to me? Anyone think that they know why? Alright, so it has to do with the strength of the gravitational force depends on the masses of the 2 objects and the distance between them. Alright, who is more massive? You or the Earth? Maddie. The Earth. No, that's why everything goes to the Earth, because the Earth has so much more mass than everything else. So that's why everything on Earth is attracted to it. Now, what is the Earth attracted to, though? Audrey. What holds the Earth in place? The Sun, because the Sun is so much more massive than the Earth. And so that's what it basically boils down to, is the mass or the stuff that makes up something. Now, occasionally, if you get so far away from Earth, you're no longer attracted to Earth anymore. Technically, that's according to Einstein's theory of relativity, it's 2 hours slightly. But technically, if you get far enough out into space, Earth's gravity no longer affects you. So that's what it's talking about with distance as well. The farther away you get, Earth's gravity gets slightly weaker the farther away you get. Now, your book does point out, though, if you go to the lowest points on Earth on land, not on the water, because that'd be stupid, but if you go to the lowest point on land, gravity is technically slightly stronger there. Like, not enough to where you will notice it, but it's where it's slightly stronger. Also, if you go, as a side note, what is the lowest point on land? My geography people should know this. And Brecken, I hope you know this. I feel like Dora talking to a camera. It's okay. Alright. Yes, Gavin. The Dead Sea, good job. What's the highest point on land? My geography people should also know this. Okay, now it's turn. You have been summoned. Mount Everest, good job. So if you were to go to the top of Mount Everest, and you were, Mount Everest is pretty steep today, and you were to jump off, first of all, jump. But if you were, would you fly off into space? No. No, you would not. You would go, whoa! And we'd probably take you to an ER because you'd probably be dead or very close to it. So, even though gravity is slightly weaker at the top of Mount Everest, it is not enough for you to go off into space. That's not how it works. But you are right that it gets slightly weaker at the top of Mount Everest. So just take a note, though, that the gravitational force is proportional to how close to the Earth's surface you are, and it also is determined by the mass of the objects. But since we're on Earth, we focus on Earth's gravitational force, or Earth pulling all of us towards it. All right. So your book points out the potential energy caused by gravitational force is the gravitational potential energy. Just make a note for that. Gravitational potential energy is a component of mechanical energy. So if it's the part of mechanical energy, what does that mean? Audrey's turn. Alright, Kendall's turn. If gravitational potential energy is a component of mechanical energy, what does that mean? What's mechanical energy mean? This is great. gravity only pulls like your leg or your arm. It affects your whole body all at once. So that's what it's talking about as well. So gravitational potential energy is a component of mechanical energy. It affects your whole body at once. Alright, at the Earth's surface, the gravitational potential energy depends on the object's mass and the height off the ground and the strength of gravity. Your book tells you that loosely average, we define the strength of gravity as 9.81 meters per second. That's how much force the gravity is pulling down on you. Again, at the top of Mount Everest, it'll be slightly weaker. At the Dead Sea, it'll be slightly stronger. This is just like an average number that scientists use for it. So 9.81 meters per second squared. That's the force of gravity, and that is pulling off you. So, potential energy, your book gives you a slightly older way of writing it. Instead of writing it PE, we do it with E with the subscript P. That just stands for energy, potential energy. It's just showing you a slightly different way of writing it. But we can stick with your book way. But just make a note that there's a couple different versions that you can use to write this. So, PE equals the mass of the object times the strength of the gravity and the height that the object is starting off the ground. So if you have an equation like this, what do you need to solve? Gavin. So if you're finding potential energy, what would you do to solve this type of equation? What's the only thing you do over and over and over again? Multiply. These equations are really straightforward. So it says, let's say you have an object that weighs half a kilogram. The strength of gravity is 9.81. Oops, that's not grams. Meters per second squared, and it starts off 1 meter off the ground. Alright, what would be the potential energy of this object? Kendall. $4.9? Okay, so what would alright, so how many sig figs? You're right that this is the correct numerical answer. Let's just fix sig figs. Alright, so how many sig figs? How many sig figs? How many sig figs? If we're multiplying, do we go off place or do we go off number? Alright, so how many should your answer have? Good job, how do I fix it? Good job, you were right with your first answer. I just wanted to just make sure. Alright, so this is energy. What's your unit? Good job. Alright, anyone have any questions about how to solve? Let's practice one more just in case. Let's say you start off with a 2.50 kilogram object. Strength of gravity doesn't change, but you start with 2.5 meters off the ground. What would this be? Noah. 61.3. Did you say anything? Okay. Alright. Good answer. So this is the correct numerical answer. Let's just fix the figs. Yes. Alright. So how many figs?
2, 3.
3. How many figs?
3.
How many figs?
2.
How many figs should this have?
3. 2.
Yes. Should have 2. So how do I fix it?
Round.
2? What?
60.
You said 61 very hesitantly. So is this it? Alright, what's your units?
2.
Like that?
Yes.
Yeah, that's it. Alright, so anyone have any questions about how to solve this? Pretty straightforward to find potential energy of gravitational force. Alright, so your book points out as well that if you were to jump from the top of Mount Everest into the ground, the strength of gravity would gradually increase because you're getting closer and closer into the Earth's surface, but you don't need to know that. Your book's just pointing out that, hey, technically it does vary slightly. Alright, anyone have any questions about that? Alright, the next major fundamental force is the weak nuclear force. There are 2 different types of nuclear force. This one's the weaker one. So this is why this one's known as the weak nuclear force, because sometimes scientists just aren't creative. So weak nuclear force, it affects subatomic particles. It's a very small range. Scientists aren't actually sure what it does quite yet. It's difficult to study because it affects such a small, narrow range. So because of that, we're not sure exactly exactly what it does. We think it causes particle decay or causes particles to deteriorate, but again, not really sure. We know it's there, but we're not sure exactly what it does. So no, do you know the italicized phrase? The potential energy caused by the weak nuclear force is usually insignificant compared to the potential energy caused by other fundamental forces, so it's less noticeable because of how short range it is. It is stronger though than the gravitational force, it's just a lot shorter of a distance. So just make a note, it's stronger than the gravitational force, it's over a smaller range, so we don't notice it as much, and we think it causes particle decay, we're just not sure. Alright, anyone have any questions about weak nuclear force? Because that's about it, because it's difficult to study. Alright, the next one is the electromagnetic force. So this one has two major components. What do you think one is, Kendall? Good job. And then what's the other one? Audrey? Electricity. So that is the major one for it. So that's supposed to say electric. I'll fix it later. So electromagnetic force is the idea of the two major ideas are electricity and magnetism. But then there's also two other parts to it that kind of affect it as well. So chemical energy and elastic potential energy as well. But the two main ones are the electricity and the magnetic parts. It's going to bother me. I got to fix it. So this first one, the electric potential energy. This one's the first major one your book talks about. Careful better. The electromagnetic force only affects objects with an electric charge. So this one affects electricity or electrical charge stuff. Now keep in mind, does everything in the universe have an electric charge? Gavin? No. So a lot of substances are neutral. Like your body in general is neutral. Now, depending on what you're talking about, there might be slight charges. Like your heart runs on electricity. Your brain runs on electricity. But overall, your body is neutral for it. So, just make a note though, the electromagnetic force, it only affects objects with an electric charge. If you're a neutrally charged object, electricity doesn't really affect you. Now, sometimes electricity will go through you, and that's potentially a bad day, but it's the idea of it's not attracted to you. Now, you might have worked with static electricity before. Anyone know what static electricity is? I'm pretty sure some of you worked with this before, or am I thinking of junior high? Alright, so how many of you have taken a balloon, you've rubbed it against your hair before, or you've jumped on a trampoline and you notice that your hair, if you're a lady in particular, your hair starts to do kind of crazy things. Okay, so you've noticed that. How many of you, if you're shuffling around on a carpet, you went up to go touch potentially a sibling or a friend to go inflict pain, basically, is what you were trying to do. Alright, that's the idea of static electricity. Whenever you take a balloon and rub it against your hair, you're having the electrons shift and move from the balloon to your hair, from your hair to the balloon. Same idea with a trampoline, because of the friction between the trampoline rubberish material and your feet, it's generating static electricity. Whenever you're shuffling across the carpet, it's generating static electricity. There is a particular carpet at my college where I went to in the library to where it would just generate static electricity all the time. Now, I would go get water from the water fountain. So the water fountain was like rubber on the outside. So whenever you would get close enough to actually drink water from the water fountain, that was close enough for the electricity to jump from you to the water in the metal water fountain. There were several times when I got shocked in the lips from it, and that was not fun. It's not a good day. But that's the idea of an electric transfer. So electric potential energy, this affects objects that have a charge on them. Do make a note though that the electromagnetic force is responsible for all known forces in the universe except for gravitational forces and some subatomic forces. Because electricity, magnetism, chemical, and elastic potential energy encompasses so many things, this one is the most widely affecting force. So make a note of that. So it doesn't affect gravity, because that's mass, and it doesn't affect the atoms and molecules. But just make a note that this force affects primarily everything else in the universe. So make a note of this, at least on Earth. So there's some kind of special applications if you go at the speed of light. But electricity, magnetism, chemical with the attractions of objects, and elastic potential energy, all of these are part of the electromagnetic force. So make a note for that. Your book points out that one of the major parts of it is with electrons. Okay, this is kind of getting into chemistry, but I think we've talked about this in junior high. Anyone know what an electron is? Okay, so you might remember protons, neutrons, and electrons. Electrons, those are the moving parts. That's the part that's actually generating electricity. It's the negatively charged part of the atom. Do you make a note of that and mark that in your book? Your book tells you what electrons are on page 77. So electrons are the negatively charged parts of the atom. They're the ones that are moving back and forth. Protons do not leave the atom unless it's having a really bad day, like nuclear fusion, and then you're having full fission technically, and that's bad. And neutrons typically don't leave either. So it's the electrons that are moving around for it. So because of that, that's what's generating a charge. Alright, electric potential energy. This is electromagnetic potential energy caused by two stationary charged objects affecting each other. We haven't talked about electric fields yet, but you hopefully know that electricity is attracted from positive to a negative charge, kind of like magnets. So they're very closely related to each other. So if you have a negatively charged object and a positively charged object, they'll be attracted to each other. If you have a positively charged object, it will not be attracted to another positively charged object. So kind of like with magnets, like charges repel each other, while unlike charges will be attracted to each other. That's the idea with electric potential energy, that the positive and negative want to balance out each other. And that's one reason why if you were to take a knife and stick a knife in a socket, don't, because you're all old enough to know better, I'm going to do that. But if you do, the electrons in the wall socket now notice that there is an easy way to get from wall socket to ground, which is where they want to go, and they will go through you. And life's bad and life's unfortunate. Did you try that, Noah? I kind of want to ask and I kind of don't. So we're going to just move on. So, but that's the reason why you shouldn't touch electric fences or anything else like that. Just because, okay, how many of you know what an electric fence is? How many of you have touched an electric fence before? Kind of want to know and I kind of want to don't. Okay, do you want to share the story? You don't have to. Alright, Noah, do you want to share the story? Okay. One of my friends dared me to touch the electric fence. Because I'm stupid, I did. But she didn't realize her parents had turned off the electric fence. So I was like, I can climb all over this now and be fine. Thankfully her parents did not turn it back on when I was on it. So, but it's one of those that, yes, electric fence, typically if you touch it, it's not fun. Because an electric fence is typically used to convince cows and horses to not go through it. So it's a lot. So you don't know, it won't kill you, but you don't want to stand there and just keep touching it either. It's not fun. I really kind of want to ask Audrey, and I don't think I want to though. Okay, just a note of electric fields. That's what the positive and negative. So that's electric potential energy. To make a note of electric potential energy differs from gravitational potential energy, and that depends on the charges of both the objects, the distance between them, and the properties of any material separating them. So it's not like with gravity where it's just the mass and the distance between the objects. This is between how strong of a charge do they have, how far apart they are, and then also what type of material is between them. And some things, the electric charge can still go through things like metal. It can't go through rubber or plastic very well. We'll talk about the reasons why for that later on. Just make a note though that with electric fields, it's a little bit different with the idea of there are three things that affect it. So how much charge they have, how far apart they are, and then also what's between them. Alright, your book will point out as well that a charged particle in motion produces a magnetic field that can exert an electromagnetic force on nearby objects. This is magnetic potential energy. This one is caused by electrons moving, and so because of that it produces a magnetic field. So this is the electromagnetic field because electricity causes magnetism. We're going to talk about that more in a later chapter. So if you're sitting there wondering, well, how does it do that? We'll talk about the reasons why. So looking at magnetism, so magnets, you have a north and south pole. So if I were to take this magnet and cut it in half, would I get a south magnet and a north magnet? Kendall, you did magnetism, I think. Are you doing magnetism this year? Alright, so if I were to take the magnet and chop it in half, do I get a south magnet and a north magnet? No, you don't. So it'll always have two poles for it. Now, whenever you have a south pole magnet, will it be attracted to another south pole magnet? You might know this from just playing around with magnets before. Alright, Maddie. No, it doesn't like it. It's kind of like with the electrons that the opposites attract. Same idea, that the opposite sides of the magnet will be attracted, south pole and the north pole of the magnet. Now, you might, depending on how strong the magnet is, you might go, be friends, and force them together. And you can, because you are strong enough, typically you have willpower to make them stay there. But typically, they will not do that. And if you hold them there like that for too long, you can actually break your magnets and mess it up because the magnets are pushing against each other, and it'll buff basically the electrons on the inside out of alignment. You act like you want to share something. Do you want to share something? You do not have to.
I was just saying that was easy to try it on the spot to do that on recording purposes. Just like
Wait, what?
If they're strong enough, you can sit there and like take the opposites and shoot them like that.
I would have to be some really strong magnets.
Yeah, almost like it.
I want to be very strong magnets. Don't do that to someone with braces. It's one of those. You have to have a really strong magnet to affect that, but you'll probably find. Now, most of the time, your braces, depending on the type of braces that you don't have enough metal per se, or it has different types of metal. Now, sometimes they use stainless steel. That's a major wire they use, but depending on what type of wire they use, it may or may not be magnetized. So I don't know if it's a good idea if you try to decide should I magnetize my braces. That's probably not something you should be going around doing. So, checking out. So, magnetic potential energy. This is caused by the magnetic field, and the force is generated from the magnetic field being attracted to each other. Alright. Anyone have any questions about electric or magnetic potential energy? Alright, I'm going to go back to this. Well, not that direction. I'm going to go back to this slide so I can talk about the last two. Alright, chemical energy. This results from the combination of atoms and molecules. So, we're going to talk about this in a later chapter, but whenever you have certain substances combined together, they can release or generate energy into the air around them. How many of you played with a glow stick before? Okay, so what's the very first thing you have to do to... Okay, that makes me nervous. Glow stick, in order to get it to start working properly. Alright, Noah.
Right.
Alright, yeah, so you have to crack it, and then typically you shake it up. Alright, why do you have to crack it?
Because you have to mix chemicals.
Yeah, so there's chemicals on the inside. So you crack it to basically separate them and break them up and get them started, and shake it up to mix the chemicals together. That starts a chemical reaction. That's why it's glowing. Now, typically it's not dangerous. That doesn't mean you should drink it, but it's not dangerous for you. What? Yeah, I've heard that. So I've never tried it because I looked at it and I decided it was a real bad idea. But they're not toxic, but you shouldn't go around drinking glow sticks either. That's also not a good idea. But that's the reason why. That's a chemical reaction, is you're basically the chemicals reacting on the inside of it. Your book points out, in some cases they can have a general reaction, in some cases they can have an explosive reaction. It just depends how the molecules are combining together. Kind of how, like, if you ever mix an acid and a base together, that's a chemical reaction. Now, it's not like explosive. It's not super dangerous in case sometimes with some people it can be, but typically it's not a dangerous reaction. Do you want to share your own? Yeah, if you want to.
I exploded the test tube.
You exploded a test tube? It wasn't one of my test tubes, was it?
No, my dad.
Oh.
Sometimes he brought home test tubes. And then I mixed so much chemicals together and just threw it at somebody. Exploded.
You threw it at somebody? It sounds like you did like a cherry bomb.
Something like that.
Don't do that. So that's part of the reason as to why chemical energy. So it can be mild, it can be dangerous. There's also one reason why you cook food. Typically you're having a chemical reaction. But if your spice is blending all together, or in some cases you just make weapons. that works, I guess. Alright, anyone have any questions about chemical energy? Alright, elastic potential energy. Elastic potential energy. Alright, something is elastic. What does that mean? Alright, there's other definitions of just stretching it. But yes, you're right, that is a basic one. Alright, Gavin? Okay, the ability for an object to come back to its original shape. So, elastic potential energy, this is whenever the object wants to go back to that optimized range, is how your book describes it, between its atoms and molecules. Depending on the type of object, it wants to stay at a certain point. So it doesn't want to be compressed together, it doesn't want to be stretched apart, so it wants to stay in that spot. So, that potential energy caused by these restorative forces is known as elastic potential energy. Alright, anyone have any questions about these four? So make a note, all of these four parts are parts of the electromagnetic force, and electromagnetic force affects the most objects. It's not the strongest, but it affects the most objects. Alright. Nope, wrong direction. Oh, that was the right direction. Alright, the last one is the strong nuclear force. The strong nuclear force is the stronger one. Alright, so the strongest fundamental force acts only within the nuclei or the nucleus of the atom. It is called the strong nuclear force. Alright, we've kind of talked about this already. So there's protons, neutrons, and electrons. Alright, so does anyone think they know, I think you might have talked about this in junior high, which one is on the center of the atom? Protons, neutrons, or electrons? Kendall. Good job. So you have an object. So like that one, you have two different colors because there are neutrons and then there are protons all together on the inside of the nucleus. The electrons are the dots that are flying around the outside of the nucleus. So they're basically attracted to it because remember, electrons have what charge, Maddie? Positive or negative or neutral? Negative. So the electrons, they have a negative charge towards them. So they're attracted into the center because protons have what charge? Noah? Neutral or positive? If you shot here. Positive. So the protons, they have a positive charge. And then that means the neutrons must be what, Gavin? Neutral. So again, the neutrons, they are a neutral charge. I'm just going to write nothing because there's no charge to them. So the electrons are attracted to the protons. So that's part of the electromagnetic force. So going back to this line, so with the idea of chemical energy, that holds the atom together because of those charges for it. So chemical energy with the idea of those electrons being held together to the atom, that's part of it. But scientists don't know in the center why protons and neutrons stick together. Because protons are what charge, Gavin. And the neutrons are what charge, Maddie. Nothing. They have no charge. Do you have a positive object be attracted to a neutral charge to a neutral object? No, we don't. So scientists do not know why this works the way it does. They have no idea why the protons and neutrons stick together. Because remember, wrong direction. The electric fields only affect objects that have an electric charge. So that's part of the electromagnetic force. So scientists look at this and go, it just does because it does. And we don't know why. And so again, I know this seems kind of frustrating. Sometimes that really frustrates students thinking, well, why does it do that? We don't know. God put some things into unfettered nature and some things we don't know how it works and we don't know why it works. So scientists just called it the strong nuclear force because it holds the nucleus together, but we don't know why it works that way. So some things we just don't understand, we don't know, we may never know. So don't let it bother you too much wondering, why does it do that? You don't know, and that's okay. So make a note, the strongest fundamental force is as the nuclei is known as the strong nuclear force because sometimes scientists just aren't creative and they're just going to call it how they see it. The potential energy caused by the strong nuclear force is known as nuclear potential energy. So make a note of that. So potential energy caused by the strong nuclear force is known as nuclear potential energy. Alright, I'm trying to do anything else for it. Nope, that's pretty much it. Alright, so your book points out, in some cases it's involved in nuclear fusion whenever you have the atom break apart. That's one reason why, since it's the nucleus splitting, that's how it generates so much energy with uranium, because the atom itself is breaking apart, and so those protons and neutrons are being separated, and that's how it generates so much energy with this type of force. It's the strongest one. Alright, your book gives you this box that lists off the four fundamental forces, and it lists them from weakest to strongest, because you want to know which one's the strongest, which one's the weakest, and also what they affect. So make a note of that. So gravitational force affects anything with mass The smaller object will be attracted into the larger object, and it's dependent on the mass and the distance. Weak nuclear force affects some subatomic particles. Don't really understand it though, we just know it's a very small range. It's stronger than gravity, but we don't understand a lot about it yet. Electromagnetic force affects basically everything else. So it has made up of the electric potential energy, magnetic potential energy, chemical potential energy, and elastic potential energy. But the strongest one is the strong nuclear force, and it affects protons, neutrons, quarks. Okay, your book does not tell you what a quark is. Does anyone know what a quark is? Not a quark. Quark. Q. Alright, anyone think they know? Alright, it's what scientists think make up protons and neutrons, and again, don't know for sure, this is a theory, but it's what scientists think make up protons and neutrons. Alright, we're done slightly early, but what is due tomorrow? So I want to make sure everyone has questions about it. What's due tomorrow, guys? The paper, the background paper. So make sure you have it. Bring your STEM project book tomorrow in case you have any questions about it. So I moved my STEM project book, but make sure that you have it tomorrow. But then also, you should bring me a background paper. So what are you bringing me tomorrow, Kendall?
Paper.
Go. What are you bringing me tomorrow, Gavin? Go. What are you bringing me tomorrow, Maddie? Go. Does it have to have a title page, Audrey? No. Alright, what are you bringing me tomorrow, Noah? Alright. Oh, Audrey, I don't think you were here for this. What do you have on WinRab that helps describe or that helps out with your grade currently right now because I entered it in last night? Anyone remember what we talked about yesterday? Help encourage you to have everything on time. Yeah, so it's the STEM project responsibility grade is what I called it. So if parents ask you, what is that? So basically what it means is you get a free 100 right now because they entered in the money yesterday. So everyone gets another 100 quiz grade. But if you're late in turning in anything, like for rough drafts, at all. So if you're late, it'll drop down. What happens if you're late the next day, Noah? It'll drop again. What happens if you're late the next day? It'll drop again. And it'll just keep going, and I'll probably start calling mom at that point to let her know now it doesn't have a paper. It's been like 3 days. So make sure that you bring it. So right now, if you want to keep that free 100, make sure you have that paper for me. So Brecken, bring me paper tomorrow. So make sure you have it. Alright, so your homework for tonight. You'll notice we finished chapter 4. You don't have the test yet. But just keep in mind that your next test is over this chapter and the next chapter. What's also special about the next test? It's the exam. So is it just over 4 and 5? It's over 1, 2, 3, 4, 5. So it's cumulative. So make sure that you're studying this and be ready for future tests. Now, keep in mind, have we had a quiz this week? I don't know. We had a reading quiz. Have we had a review quiz this week? No, we're finishing up the chapter. So what does that probably mean?
Absolutely a test tomorrow.
Okay, goodness. But you should probably study because if it's not tomorrow, then it'll be Monday. So make sure you're studying. But no one likes Monday quizzes because Monday tests don't go so well. So we need to make sure that we're ready. Alright, so your homework for tonight. Read pages 80 through 83. Plus 85 for a second. 80 through 83. Answer page 85. Questions 1 through 7 and think. It's not that bad. Read pages 80 through 83. Answer page 85. Questions 1 through 7 and think. Alright, think back over it. Which force is the strongest force? You have a 1 in 4 chances of guessing correctly. Maddie. Yes. What? S?
Oh,
Strong nuclear force. Which of the fundamental forces is the weakest? Audrey. Good job. So, the gravitational force. What is the force that affects some nuclear particles? We don't understand a whole lot about it yet because it's over such a small distance. Gavin. Weak nuclear force. Weak nuclear force. And then what is the force that affects the most stuff, but it's not the strongest? Electromagnetic force. Study. 5.